Limits at plus and minus infinity and horizontal asymptotes. Limits at plus and minus infinity. If f of x becomes arbitrarily close to a number p for all sufficiently large positive x, we say that p is the limit of f of x as x approaches infinity, and we write limit as x approaches infinity of f of x equals p. If f of x becomes arbitrarily close to a number q for all sufficiently large negative x, we say that q is the limit of f of x as x approaches negative infinity, which we write as the limit as x approaches minus infinity of f of x equals q. To illustrate these ideas, let's consider the function whose graph is shown here. The middle portion of the graph is omitted because it's not relevant to either the limit as x goes to infinity or the limit as x goes to minus infinity. The number p indicated here is the limit of f of x as x goes to infinity. Notice that an open interval centered at p corresponds to a horizontal strip in which the graph lies for all sufficiently large positive x. This remains true as the width of that open interval, and thus the width of the strip, decreases. All of this essentially means that the function is approximately constant for large positive x. In other words, the graph approaches a horizontal line, which we call a horizontal asymptote. In this case, a rightward horizontal asymptote. The number q indicated here is the limit of f of x as x approaches negative infinity. Notice that an open interval centered at q corresponds to a horizontal strip in which the graph lies for all sufficiently large negative x. And this remains true as the width of that open interval decreases. So the function is approximately constant for large negative x, and the graph has a leftward horizontal asymptote. In summary, if the limit as x approaches infinity of f of x equals p, then the line y equals p is a rightward horizontal asymptote. If the limit as x approaches negative infinity of f of x equals q, then the line y equals q is a leftward horizontal asymptote. Examples. Let's consider first the function f of x equals x plus 1 over x. Here's the graph of that function, and notice that the line y equals 1 is both a rightward and a leftward horizontal asymptote. So the limit as x goes to infinity of f of x equals 1, and the limit as x goes to minus infinity of f of x equals 1. To understand a little bit better why both of those limits are 1, notice that the function can be rewritten as 1 plus 1 over x. When x is large, whether positive or negative, 1 over x is small, and so the value of the function is approximately equal to 1. We point out also that there is a vertical asymptote at x equals 0 because of the fact that the function has infinite one-sided limits as x approaches 0 from the left and the right. Another example. F of x equals 1 over x squared plus 1. Here's the graph of that function. Notice that y equals 0 is a horizontal asymptote, both rightward and leftward. And so the limit as x approaches plus infinity is 0, and the limit as x approaches minus infinity is also 0. Here's a bit more complicated rational function. F of x equals 2x cubed minus x squared minus 2 divided by x cubed minus 1. Here's the graph of that function. And here, the line y equals 2 is both a rightward and a leftward horizontal asymptote. So the limit as x goes to infinity of f of x equals 2, and the limit as x approaches minus infinity of f of x equals 2. Now, to get a sense of why exactly those limits turn out to be 2, let's notice that the function can be rewritten as 2 minus x squared over x cubed minus 1, either by long division or by separating the fraction into two terms appropriately. Since the second term is a proper fraction, that is, the degree of the denominator is larger than the degree of the numerator, that fraction will be small when x is large, since the denominator will be much larger than the numerator. And so for large positive or negative x, f of x will be approximately equal to 2. Now notice also that we have a vertical asymptote at x equal to 1 because that's where the denominator is equal to 0, and the one-sided limits as x approaches 1 are both infinite. Here's another example involving a rational function. Here's the graph of the function. The line y equals 3 is both a rightward and a leftward horizontal asymptote. So the limit as x goes to infinity of f of x equals 3, and the limit as x goes to minus infinity of f of x is also 3. And notice that the function can be rewritten as 3 plus the proper fraction 3x over x squared plus 1. Now all of the examples we've shown so far have corresponding rightward and leftward horizontal asymptotes. That is, the limit as x approaches plus infinity and the limit as x approaches minus infinity coincide. Now here's an example where that's not the case. Let f of x equal x divided by the square root of x squared plus 1. Here's the graph of that function. Notice that y equals 1 is a rightward horizontal asymptote, while y equals minus 1 is a leftward horizontal asymptote. The limit as x approaches infinity of f of x is equal to positive 1, while the limit as x approaches negative infinity of f of x is equal to negative 1. Now let's consider f of x equals sine of 2x minus x over the square root of x squared plus 1. Here's the graph of that function. And here, y equals 1 is the leftward horizontal asymptote, while y equals minus 1 is the rightward horizontal asymptote. Notice how the graph oscillates about each of these horizontal asymptotes. The limit as x approaches infinity here is minus 1, while the limit as x approaches minus infinity of f of x is plus 1. Now let's consider the simple cubic polynomial 6 plus 7x minus x cubed. Here's the graph of that function. The graph has no horizontal asymptote, but still we can use the language of limits at plus and minus infinity to describe the behavior of the function for large values of x. Here we say that the limit as x approaches minus infinity of f of x is plus infinity, while the limit as x approaches positive infinity of f of x is minus infinity. These statements simply describe the direction in which the tails of the graph go. Let f of x equal x times 1 plus x minus the absolute value of x, all divided by the square root of x squared plus 1. Here the graph has a rightward horizontal asymptote, y equals 1, but it does not have a leftward horizontal asymptote. Notice here that for negative values of x, the numerator of that fraction is equal to x times 1 plus 2x, while for positive x, the numerator is simply equal to x. Here the limit as x approaches minus infinity of f of x is plus infinity, while the limit as x approaches infinity of f of x is equal to 1. For an example in which limits at plus and minus infinity not only don't exist, but cannot be described as either plus or minus infinity, let's consider f of x equals cosine x. Here the function is bounded between minus 1 and 1, and oscillates between minus 1 and 1 as x gets larger in either direction. And so we can only say that the limit as x goes to infinity of f of x does not exist, and the limit as x approaches minus infinity of f of x does not exist. Here's another example in which neither of the limits at plus and minus infinity exists. F of x equals x cosine x. Here the limit as x goes to infinity of f of x does not exist, and the same is true for the limit as x goes to minus infinity. Calculation of limits at plus and minus infinity. Some basic limits. For any p greater than 0, the limit as x goes to infinity of 1 over x to the p is equal to 0. And if x to the p is defined when x is negative, the limit as x goes to minus infinity of 1 over x to the p is equal to 0. Now let's look at an example to see how these limits are used. Let f of x equal the rational function 3x cubed plus x squared minus 5 over 2x cubed minus x plus 1. Let's find the limit as x goes to infinity and the limit as x goes to minus infinity of f of x. We'll first multiply the numerator and denominator of our fraction by 1 over x cubed. The numerator then becomes 3 plus 1 over x minus 5 over x cubed divided by 2 minus 1 over x squared plus 1 over x cubed. Now we notice that each of the reciprocal powers of x in our expression approach 0 as x approaches infinity or minus infinity. Consequently, the limit as x goes to either plus or minus infinity of f of x is equal to 3/2. Here's another example. Let f of x equal x squared plus x plus 3 over 5x cubed minus 1. Notice here that the degree of the denominator is now larger than the degree of the numerator. Here, we'll again multiply the numerator and denominator by 1 over the highest power of x in the denominator, 1 over x cubed. The numerator now becomes 1 over x plus 1 over x squared plus 3 over x cubed, and the denominator becomes 5 minus 1 over x cubed. Now again, each of these reciprocal powers of x approaches 0 as x goes to plus or minus infinity, and so f of x approaches 0 over 5, or 0, as x goes to plus or minus infinity. Another example, let f of x equal x cubed minus x squared plus 3 over 3x squared plus x minus 5. Notice here that the degree of the numerator is now greater than the degree of the denominator. Now let's find the limit as x goes to plus and minus infinity of f of x. We'll take the same approach as before. We'll multiply the numerator and denominator by 1 over the highest power of x in the denominator. This time the numerator becomes x plus 1 plus 3 over x squared. The denominator becomes 3 plus 1 over x minus 5 over x squared. Again, the reciprocal powers of x go to 0, leaving x plus 1 over 3, which simply becomes larger and larger as x gets larger and larger, and so our limit is plus infinity as x goes to plus infinity, and minus infinity as x goes to minus infinity. Now let's think about rational functions in general. Suppose that f of x is a rational function whose numerator is an nth degree polynomial with coefficients a0, a1 through am, and whose denominator is an nth degree polynomial with coefficients b0, b1 through bn. We'll multiply the numerator and denominator by 1 over x to the nth power and obtain an expression in which the first term in the denominator is the constant bn. Notice that all other terms in the denominator involve negative powers of x, which will approach 0 as x goes to either plus or minus infinity. So those negative powers, along with whatever negative powers appear in the numerator, approach 0 as x goes to infinity, and the value of the function will be approximately equal to the leading term in the numerator divided by bn for large values of x. How this behaves for large values of x depends upon the exponent m minus n. If m is less than n, then the numerator involves a negative power of x, which would approach 0 as x goes to either plus or minus infinity. If m is equal to n, then that fraction is simply a sub m divided by b sub m, which will be the limit as x goes to either plus or minus infinity. If m is greater than n, then we have a positive power of x in the numerator, and so the limit will either be plus infinity or minus infinity. So we have three cases. When the degree of the denominator is greater than the degree of the numerator, the limit as x goes to either plus or minus infinity will be 0. If the degrees of the numerator and the denominator are the same, then the limit as x goes to either plus or minus infinity will be the ratio of the leading coefficients. If the degree of the numerator is greater than the degree of the denominator, then the limit doesn't exist and the function will approach either plus infinity or minus infinity as x goes to either plus infinity or minus infinity. Now let's note that it's not necessary that m and n be integers here. For example, the limit as x goes to infinity of 5x to the 4/3 power minus x to the 1/2 power over 3x to the 4/3 power minus 7x plus x to the 2/3 power will equal 5/3. That is, the ratio of the coefficients of the highest powers in the numerator and denominator, since those powers are the same. Now let's look at a few examples involving functions that are not rational functions. For instance, let's find the limit as x approaches infinity and the limit as x approaches minus infinity of the function f of x equals 3x minus twice the absolute value of x divided by x plus 2. The first thing we want to notice is that if x is positive, absolute value of x is the same as x, and so the numerator of the fraction is identical to 3x minus 2x, or just x. If x is negative, then the absolute value of x is equal to minus x, and so the numerator of the fraction equals 3x plus 2x equals 5x. Now let's notice that each part is a rational function whose numerator and denominator have the same degree. So the limit as x goes to plus infinity is equal to the limit as x goes to infinity of x over x plus 2, which will equal 1, the ratio of the leading coefficients. As x goes to negative infinity, the limit of f of x is the same as the limit of 5x divided by x plus 2, which will be 5 divided by 1 equals 5. Here's another example. Find the limit as x goes to infinity and the limit as x goes to minus infinity for the function f of x equals 3x minus 7 divided by the square root of 5x squared plus 4. Let's first factor in x squared from the two terms inside the radical in the denominator. 5x squared plus 4 is equal to x squared times 5 plus 4 divided by x squared. Now let's rewrite the denominator as the square root of x squared times the square root of 5 plus 4 over x squared, and rewrite the square root of x squared as the absolute value of x. Now let's multiply the numerator and denominator of this fraction by 1 over x. For positive x, the absolute value of x times 1 over x will equal 1, and so for positive x, the function becomes 3 minus 7 over x divided by the square root of 5 plus 4 over x squared. Now, as x goes to positive infinity, 7 divided by x and 4 divided by x squared each approach 0, and so the limit of our function as x goes to positive infinity is equal to 3 over the square root of 5. For negative x, the absolute value of x times 1 over x is equal to negative 1. Therefore, our function for negative x equals 3 minus 7 over x divided by minus the square root of 5 plus 4 over x squared. Now again, 7 over x and 4 over x squared each go to 0 as x goes to minus infinity, and therefore as x goes to minus infinity, f of x approaches minus 3 over the square root of 5. One final example. Let's find the limit as x goes to infinity of f of x if f of x is equal to the square root of x plus the square root of x minus the square root of x. The first thing we'll do here is multiply our function by a fraction whose numerator and denominator are both equal to the same expression that defines f except with a plus sign between the two terms. This lets us rewrite the function with a denominator of the square root of x plus the square root of x plus the square root of x, and with a numerator that's equal to x plus the square root of x minus x. So we simplify and obtain square root of x over the square root of x plus the square root of x plus the square root of x. Now let's multiply the numerator and denominator by 1 over the square root of x. This gives us 1 divided by the square root of 1 plus 1 over the square root of x plus 1. Now since 1 over the square root of x goes to 0 as x goes to infinity, f of x will approach 1 over 1 plus 1, or 1/2, as x goes to infinity.